Okay, so pressure in a liquid, pressure inside a liquid at rest. What is pressure inside a liquid at rest? Is the force or the thrust force on unit area inside the liquid. That means, say there is a vessel, and vessel containing a liquid. So suppose at a certain point there is an area, right? Say if you zoom out of this thing, suppose there is an area like this, vertical. So this vertical area will experience a force F, or rather say dF, and if it is a very small area, dF, and this is dA. dA is area and dF is the force experienced by this area. And suppose this maybe in this direction as well, dA, then the force from this side, that's dF, or maybe in this way, area is dA and the thrust force is dF, this area. In each case, this dF by dA is equal to small p. This small p is at the point, pressure at the point inside the liquid or inside the fluid, or the fluid. If you go to swim inside water, you will feel the normal force on yourself from all sides. I mean, no part of the liquid will pull you, right? Liquid will uh, push you from all sides. That's the thrust force. Thrust force is, so actually thrust force is compressive normal force. So if you keep a block inside liquid like this, so if you keep a block inside liquid, the block will be pushed from all sides. Push from here, push from here, here and here, from all sides. No, no part of the liquid will pull it. That's thrust force. So any area you have, and suppose the thrust force is dF, and the corresponding area is dA. So this dF by dA is equal to pressure at this point. I mean, if this is a very small body, then you consider this dA as the area and dF as the thrust, a small thrust force on the small area. That is how you calculate pressure at a point. To calculate pressure at a point, you have to make the body very small, almost length, breadth and height are very small. That is what a point is all about. Okay, now we will derive difference in pressure between 2 points in a liquid, in an isotropic liquid. I'll explain this thing. In an isotropic liquid at rest. Isotropic means same properties throughout the volume. That means the we mean to say that the density is constant. Density is uniform throughout its volume. Doesn't happen for a gas. So density is constant. Density is denoted by rho. right? Density is denoted by rho. It has the SI unit of kg per meter cube, right? Difference in pressure between 2 points in an isotropic liquid at rest. So consider the isotropic liquid in a vessel, and let's consider 2 points here. So in the same vertical level, consider 2 points, say A and B. Say A and B are points in same vertical line, and this thing is H. So we have to calculate PA minus PB. So here you consider a cylinder, a very thin cylinder. This is end B and end B. Consider a very thin cylinder made of the liquid itself, having the height H. And suppose the cross section is alpha. Alpha is cross section. So from the top part, the thrust force is PB into A, PB into alpha rather. From the bottom part, the thrust force is PA into alpha, and the weight is H alpha rho g, if rho is the density of the liquid. Now, for equilibrium of the cylinder, for equilibrium of the cylinder, the liquid is at rest, and so the cylinder made of the liquid is also at rest. So the forces will balance. So PA into alpha is equal to PB into alpha plus H alpha rho g, implies PA minus PB equal to H rho g. So this is the difference between pressure, or difference in pressure between 2 points. H alpha, H into alpha volume, volume into rho mass, mass into g weight. So H alpha rho g is weight of the cylinder. Okay, so that was pressure difference. So what will be absolute pressure? Absolute pressure of liquid at a depth h below free surface. So absolute pressure of a liquid at depth h below free surface. See, if this is exposed to atmosphere, the there is atmospheric pressure. Generally, we denote by P naught as atmospheric pressure. The, so Earth is surrounded by the huge atmosphere, huge atmosphere layer surrounds the earth, and that is also attracted towards the center of the earth by its gravitational force. So this will exert a force, obviously. This will exert a force, and the weight due to that force, and due to that force you have this atmospheric pressure on the surface of earth. As you go above the surface of the earth, obviously the atmospheric pressure will decrease because you have lesser of atmosphere on top of you. So here, by the way, at the surface of the earth, the atmospheric pressure is P naught, right? So that will act on the free surface. And say you want to find at a depth h the absolute pressure. Now, just outside the liquid surface, it is atmospheric pressure. So just inside also you have atmospheric pressure. Now here you have pressure P. So in the same way we can write P minus P naught is equal to H rho G. So P minus P naught is equal to H rho G. Now this is a thing that why see, atmospheric pressure is the pressure outside the liquid surface. So why inside the liquid surface it will be same as P naught, because we have derived the formula for difference in pressure between 2 points inside liquid. So the 2 points there, this is inside liquid which is having pressure P, and the outside and this point also just beneath the free surface, this is also having P naught. I mean just on the free surface, right? Surface is the uh, something which is separating the liquid from the atmosphere, or I mean the atmospheric layer or air outside, that will exert P naught. But why this is also P naught? Why this is also P naught? So this we'll discuss in details in a later topic known as surface tension. But you remember one thing: if the surface is flat, if the surface is a flat surface, there can be three types of surfaces: flat and curved in this way, right? Or curved in that way. Outside it is atmosphere or air. Here outside it is atmosphere or air. Outside it is atmosphere or air. And inside it is liquid for all the cases. Now, for the flat surface, outside pressure is P naught and inside pressure is also P naught. Now, for the curved surface, shown in, say, let's name the figures 1, 2 and 3. For figure 2, outside pressure is P naught, inside pressure is, say, uh, P. So here P, or suppose P2. Say let this be as it is figure 1. So P1. So P1 is equal to P naught. So P2 at a point on water or liquid, just I mean on the surface or just below the surface. So this P2 will be less than P naught. P2 will be less than P naught. And here in third figure, P naught outside and just inside the liquid it is P3. Here, as you can notice from the shape, this P3 is greater than P naught. So later on in a topic of surface tension, we will see that the surface of the liquid acts like a stretched piece of cloth or a stretched membrane. So if this is a certain part of the surface, so there is a tension force like in a string. Its surface acts like a piece of cloth. So this is the tension from both sides, from all sides rather. So as you can see that the net force of tension is upward, and so this pressure act downward from atmosphere, and here it is P2. So obviously due to this disbalance, due to the vertical component of this tension, the force P naught is greater than P2. So that the details will study later on in the topic of surface tension. By the way, we know that for a flat surface it works like this. So we can write P minus P naught equal to H rho g. As P minus P naught is equal to H rho g, so P is absolute pressure is equal to atmospheric pressure plus H rho g. Now there is a term that P minus P naught. This is known as gauge pressure. So uh, gauge pressure at the point is obviously equal to H rho g. So also there is a point that see if the vessel is accelerating upwards. So if the vessel accelerates upwards up at A is the acceleration. Then suppose there are these 2 points A and B. I don't know in the previous diagram which one was below A or B. However, let it be like this A and B, and the vessel is accelerating upwards. So you have to find PB minus PA. PB minus PA is how much? So either you can solve from the frame of the vessel or ground frame. So first you have to consider a cylinder which no one else than you can see because it is made up of the liquid. So their force is PA, is the cross section is alpha, and their PB into alpha, and the weight is H alpha rho g. And if you solve from ground frame, then PB alpha minus PA alpha minus H alpha rho g is equal to mass times acceleration. So mass is H alpha rho times A. So therefore you get PB minus PA is equal to H rho times G plus A. So this is the expression for pressure difference between 2 points inside an accelerated liquid. So suppose you have a liquid at rest. If you have a liquid at rest, then in the same horizontal level, all points have same pressure, equal pressure. So that is quite obvious why all points have same pressure, because you can see it is H rho g, right? And the surface will be horizontal, no shear force this way. You can explain in this way, or if you want to explain in a different way, let's consider 2 points A and B in the horizontal level, and you can consider a cylinder, and the cylinder doesn't move. So this way the force is Pa into alpha, and from the right force is Pb into alpha. Obviously, the cylinder doesn't move, so Pa into alpha is Pb into alpha, implies Pa equal to Pb. So even if it has a curved shape, it doesn't affect, because even if because due to surface tension, later on we will learn that there is a meniscus form. Then also at all points in the same horizontal level, you have same pressure, because if you consider the cylinder, the shape, the meniscus doesn't affect the equilibrium of the cylinder. So if there is say P1 into alpha from here and P2 into alpha from here, so obviously P1 equal to P2. So from that we can conclude that for all points in the same horizontal level, there is same pressure. One more important point is that pressure at a point inside a liquid or a fluid is same along all directions. So there is a proof of this. In order to prove that, suppose this is a vessel and this is a point. So so one more thing, pressure at a point inside liquid is same along all directions. So for that we, so inside the liquid we consider a very small prism inside the liquid. Consider a very small prism inside the liquid at this point. If you zoom out of this point, you see this prism is there having a certain angle theta. The area is A, this face has area A sine theta, this face has an area of A cos theta, and suppose the pressure from this side is P, so this force is Pa. Pressure from the vertical side, suppose it is P1, so this is P1 multiplied by A sine theta, and pressure from here be P2, so P2 into A cos theta. Now this is a very small prism, so we can neglect its weight, so that the components of the force Pa will be this. If this force is Pa, total force, so this angle is theta, so that's Pa cos theta, and that's Pa sine theta. And for equilibrium of this prism, for equilibrium of the prism, we can write Pa sine theta is P1 A sine theta, and Pa cos theta is P2 A cos theta. So from these two equations, what do you get? P is equal to P1 equal to P2. And actually that proves our point that pressure is same along all directions. We have considered pressure say at this point, it's P from here and P1 from here and P2 from here, and now we have proved that this is same. P is equal to P1 equal to P makes angle theta with vertical in this way. See, we have dealt with this case in a previous lecture. So how to find out the angle theta made by the liquid surface is the vessel is having an acceleration A in horizontal direction. This is a vessel is moving on surface, a horizontal surface. How to find out theta? In an alternative way, you can find out. Let's consider two points in same horizontal line. A, suppose A and B. So let A and B be two points in same horizontal line, and suppose the length is L. So we can consider a cylinder. consider a thin cylinder of length L and cross section alpha, very small cross section alpha. Yes. No one else than you can see the cylinder, because it is in your mind, the cylinder, right? No one can see the cylinder made of water inside water. So the force, now we are considering the force equation on the cylinder. So from the left equal, it's Pa into alpha, from the right it is Pb into alpha, and the heights are different. As you see, the heights are different, Ha and Hb. So this height is Ha from the free surface, and this height be Hb. So suppose it is actually flat surface. So Pa, absolute pressure, you can find Pa is equal to P naught plus Ha rho g, and Pb also P naught plus Hb rho g, right? So Pa alpha minus Pb alpha, I mean for the cylinder, if you apply force equation on the cylinder, then Pa alpha minus Pb alpha is, what is the mass of the cylinder? L alpha into rho times acceleration A. So implies Pa minus Pb is equal to L rho A. Now we'll substitute the values of Pa and Pb at calculated. So Pa minus Pb is Ha minus Hb rho g is equal to L rho A, implies Ha minus Hb divided by L is equal to A by G. Now if I consider a triangle in the diagram, I have to consider a triangle this. So inside this triangle, the angles of the triangle is, so this angle of the triangle is theta, the base angle, and if you draw the sides of the triangle, the height of the triangle is Ha minus Hb, and the base of the triangle is L. So from here you can calculate tan theta is Ha minus Hb divided by L. Now we can equate that, implies we can equate this expression and this expression, implies tan theta is equal to A by G. So we can find out the angle made by the liquid surface with the horizontal. So the same problem we have done before, to find the equation of the liquid surface. So y as a function of x. Here we'll do by a different approach. Here we'll consider a cylinder, this cylinder, and the length of the cylinder will be x, and the height, this height will be y, obviously the y coordinate, because the point on the surface, the point on the surface is having coordinates x and y. So we consider this horizontal cylinder below it in this way. So one end of the cylinder you have atmospheric pressure because outside it is P naught. So I will draw the cylinder again here. This cylinder is in a circular path. Cylinder moves in a circular path at angular velocity omega, and this is the axis of rotation. So as you know, the force, and suppose the cross section is alpha, so this is P naught into alpha, and from the right side P naught plus y rho g multiplied by alpha. Now for a rigid body like this, you have to consider, when you apply Newton's law on the rigid body, you have to consider its center of mass. Its center of mass is at a distance x by 2 from the axis, and center of mass is in circular path of radius. So the center of mass of the cylinder is in circular motion of radius x by 2. So acceleration of the center of mass is, obviously the acceleration of the center of mass is uh, in which direction? See, obviously it is towards the center of the circle. So we can draw the acceleration of the center of mass is towards the center of the circle. So this is ACM. So ACM is radius times square of the angular speed, omega square. So now you apply Newton's law on the cylinder. P naught plus y rho g into alpha minus P naught alpha is equal to x alpha rho times ACM. So that means y rho g alpha is equal to x alpha rho times ACM is x omega square by 2, implies you can write this y is equal to, alpha will cancel, rho will cancel, omega square x square by 2g, and this is the same thing we have derived before in a different way.